Alright, time for another DraftPhysics.com video presentation. So I think I will deal with a comment by the raphaelhythloday. So he has answered the video I made with a substantial comment. So it is unfortunate people can't do this interactive thing in a more practical way of being able to draw what they're arguing and that kind of thing, but whatever. That's all we get. That's all we get. So I will preface by again going over what's being disputed is Newton's corollary, okay, describing his laws and explaining a circumstance that clarify. All right, and obviously, like I said, he couldn't put in as many drawings as he would have liked because drawings were expensive. They had to carve them into a wooden block and all that kind of crap. So anyway, can't do it like this. Didn't have this advantage of the interactive live human book. Yeah, no. And unfortunately, current people aren't able to use it. So I would argue that Newton's just creating a circumstance. So we just have a universe, so to speak, a little verse. And he's basically saying that we're going to put two things in this universe. Okay, we're going to have an object that we'll call B, okay, and an object A. An object A will be 3 times the mass. So this is a 1 mass, this is a 3 mass. All right. And this one's going to have 2 units of motion. Okay. And this one's going to have, now they could be in the same direction or they can be in opposite directions. I don't think it really matters, but let's make them in the same direction just for the sake of being careful. All right. So this has a velocity of 2 and this has a velocity of 10. All right. So this has a momentum of 10 total. This has a momentum of 6 total. All right. So if you can keep those numbers in your head, everything will work out just fine. And his argument is let's just take them as objects. And so if this object ends up transferring its energy to the system, okay, it bounces off the wall. It doesn't matter how it does it. It's going to lose what it has. So it has a 10 velocity. And we can make it go all the way down to 0. So it stops moving. Okay, so we kill this 10. And the 10 is transferred. It has no choice. The only other object in this thing is this object. It has to acquire that 10 in momentum, which means that its velocity, okay, has to increase to 5.3. And this is what Newton describes. Now, he doesn't give you this velocity number, but you can calculate it simply enough. And so he's basically just saying, oh, here, this is the number, yeah. So it lost its momentum. It's now stationary. It's dead in the water. And this has the 16. He's talking, okay, it's conservation of momentum. Now he says, he qualifies his statement, if I may say so. So he's basically saying, let's, what if, okay, or, that kind of thing. And so he's basically just saying, let's imagine, okay, that this, even though it had 10 going this way, let's say that now it has 1 or 2 going this way. So we'll just use the 2 example. So it has 2 going this way, right? Well, that's momentum, not velocity, sorry. Okay, so it's gained 2 momentums going this way, all right? So the velocity would be 2, okay? So it's not that complicated. And the momentum would be 2. So it now has 2 in this direction. Well, the only way it can get 2 in this direction is this, the other object, has to go 2 in this direction. So it has to gain from the 16, it has to go to 18. Because that's the only way this can go this way, is this has to get more energy that way. Okay. And so now this is up to 18, okay, and this velocity is up to now 6. Because it's a 3 mass. And that's basically what he's saying, okay, is that what if we, what if? I mean, we did the experiment where we took all of this energy and put it into this object. Well, now let's say it's took all the energy this way and now it's going the opposite direction. Well, we have to account for that, and that means it has to be over here. Okay, and that's all he was saying. So it's still, everything he's saying says you have to have a total of 16, except, yeah, and you still have a total of 16, right? You have 2 going this way and you have 18 going this way. So obviously the 2 subtracts from the 18, you go back to your 16 original. So you had 16 originally going this way, and you still do have 16 going this way, minus the 2 going the wrong way. So the whole system, right, you could argue if you thought of it as a whole system, the whole system is still going 16 this way. So all the energy has been conserved, and he's just creating a what ify. Okay, so that's really what he's saying. So nowhere in this at all is there any indication he's saying you can make more momentum, that the total net momentum or motion in the system can ever increase. He's saying overtly you can never increase the net momentum. The number, the length of arrow cannot be increased. All right. All right. So, yeah, an attempt to clarify. And again, the text, he repeatedly talks about how you have to conserve the 16. So clearly he is introducing energy to create the motion in the opposite direction. Obviously he had a dead object. It can't just, there's no place he describes it as getting this extra energy, and that's why he qualifies it by saying, if I may so say. I mean, he qualifies the fact that he's breaking the rule of his experiment. All right. I understand your point that Newton was spitballing the values to make a point of conservation of momentum. So he doesn't get that point, because what he's going to do is just defend everything he said. So he obviously doesn't get the point. Newton was not a Leibnizian. He did not believe in 1/2 mv squared. He didn't believe in mv squared. It wasn't part of his physics, any part of his physics. Okay. Under ideal conditions, there should actually be one outcome in a perfect elastic collision. His whole argument, what Newton's saying is these are perfectly elastic in the sense that he's accounting for nothing. No friction, no pieces break off, there is no deformation, there is no place that the energy is absorbed. So nothing is absorbed going some other direction. It's just 2 objects with energy, momentum, and that momentum has to always be conserved in motion. There is no losses to any other mechanism. So that's a moot point, frankly. Close to that of hardened objects of definite mass and velocity. Yes. Okay. I suppose the variety of his values comes from the variability of the substance from which the objects may have been constructed. So that's exactly what he's not saying. There's absolutely no room for wiggling about substance, what the substance are made out of. There's no possibility of generating any extra anything or destroying anything through deformation or heat or any other losses. So it's clearly a lossless situation. And so all of these excuses to say that he's implying that something consumed energy, he's clearly implying the exact opposite. He's clearly stating nothing is consumed. He does not make a distinction between inelastic and elastic. Well, he's clearly making the distinction, and he's saying to you, these are perfectly elastic. That's obviously what he's saying. Yet, of course, some momentum would be lost on more yielding substances. It is problematic. There's no problem. He's clearly stated in the premise that this doesn't have anything to do with inelasticity. Okay, this doesn't have anything to do with breaking or deforming or scattering or in some other way deflecting the energy into some other location. I can see the flaw in my reasoning. He doesn't see any flaw. Okay, that him proposing a deduction of momentum to make the whole is not proof of a carried experiment or for any momentum difference proposed that may be conserved. So I don't know exactly what that says, so we'll just forget it. You allude that it may be something extra that pushes them apart. I allude to the point that Newton is saying, look, if I may so say, if I may break the rules of the experiment a little bit and say, what if, okay, it not only lost all 10 of its motion, but now it's actually moving in the opposite direction. Well, if it's moving in the opposite direction, then the other object has to be going the other way, because that's the only way it could possibly be going that way, is it had to in some way interact with something that did the equal and opposite reaction. Let's understand he's defending his own reasoning of his own laws, both 1 and 2, in this colliery. That's what he's defending, are those two laws. You may say that he is not saying the following: you can make an object go 18 and the other go 2. He's not saying that the 10 object has the capacity to give something 18. Yes, that's what he's clearly saying, is that the momentum, the 10 that it started with, is all it has to give. And he clearly stated that when he explained that when it gave away all of its motion, it doesn't have any more. It stopped moving. It obviously can't give more than the 10. All right, given the total momentum is 16 to start with, but there is no talk of introduced momentum, so there is talk of it by saying, if I may so say. So why would he put that qualification in if what he was going to say was, oh, it's perfectly reasonable for us to understand that it has 10 going this way, and all of a sudden it produces 2 going the opposite way. Somehow that makes sense. When no, of course it wouldn't. By something like a spring or an explosion. Being unmentioned, it would be really sloppy and confusing. Well, the fact that it's first been translated out of Latin, okay, and so who knows how much of it we get, is preserved in terms of understanding. Yeah, I mean, there's lots of people that say Newton's not an easy read. Okay, to inject this extra momentum without a word while being very clear that momentum is conserved, right? Okay, so you're conceding the very clear part, that momentum is conserved, that nowhere is he indicating there's some other kind of energy, all right, that somehow reveals itself. All right, therefore I infer that it is speaking about the momentum difference, 18 minus 2 equals 16. Yes, so the system can't possibly gain any more momentum. Let's understand that the colliery starts with the italicized words, where he's basically saying, kind of overtly, that any system, okay, cannot gain or lose energy, that it's a closed system, that the momentum in that system will always remain the same. So you can put any kind of objects in it and you just total up what the objects are all doing, and that number will always be 16, for example. He's clearly stating that the motion in the system will always have to equal 16 as a whole, rather than it being more momentum as you pose, for merely as a theoretical illustration to emphasize. Well, he's clearly doing it to emphasize that, yes, even if we can imagine the object loses all of its energy in one direction, and now we're going to give it energy in the opposite direction, we have to account for that energy. So if it acquires energy in the opposite direction, something else in the system has to have energy in the opposite direction. That's all he's really saying, is that if something's doing something, you can look at everything else in the system and say something else in the system has to account for that. Now, I would argue that, Newton's laws are not perfect in the sense that I would describe them differently, that all things are doing is exchanging their condition, and that you don't need any opposite reaction. There's no opposite reaction. There's just the action of you giving your energy to something. And the fact that you gave it away means you don't have it anymore, which means that you have energy in the opposite direction because you were in balance. So if I'm standing still, it means I have the same amount of this as I have that. If I open a hole and I let that out, then I'm going to have a bunch of this that's going to push me. I'm going to have an imbalance, a dimensional imbalance in my motion. All right. Yes, he did not say a one mass has 100 Yes, he did not say that the one mass has 100 momentum. Well, he clearly said it has a momentum, so whether we call the number 100 or not doesn't matter. Crashes into a 3 mass and gives it 150. Okay, he clearly didn't say that, right? So he clearly isn't indicating any belief that there's a squared function to the velocity. And that's all we need out of this, is some concession that Newton doesn't, he doesn't factually imply it, okay, or state it. And it's, you have to really reach for it to claim that there's some reason he's giving some latitude to it, because he's really not. He said 16 and gave 18, but it's analogous, albeit divorced from any actual experiment. Well, we already know it's divorced from any actual experiment because we can't do the experiment where we take a light thing and give all of its energy to the heavy thing. We don't have a mechanism for doing that. There's no mechanism that will make the transfer, short of something like a lever. And then you have to compensate for the weight of the lever. So that'll be another video to go over that crap again. Because based on his reasoning, if an object with 100 gives 150, it has to bounce back with 50. The argument would be, yes, that obviously you'd have to account for it having energy in this direction, okay, but then we're back to analogizing this to brick walls or something. And would Newton say that, if I throw a rubber ball against a wall, that I've put twice the momentum into the wall? I think Newton would understand if the wall doesn't yield, I'm getting back the energy I put in. That is, 150 minus 50 equals 100. The initial total momentum. Of course, in an experiment there's no way for you to do that experiment, frankly. There's no way for you to sit there and throw something, okay, a light thing at a heavy thing in a Newton diagram and have it bounce back and put twice the energy into the object. That just ain't going to happen. Of course, an experiment should be the only recourse to determine the values rather than assumed momentum transfer. Well, of course, there should be experiments, and there aren't any. So the very fact that physics hasn't even done this with a Newton's cradle. They have all these high-speed cameras, all this other crap. They can't even just take a Newton's cradle with the 1 mass and the 3 mass and do the frickin' experiment in a clinical way. And all this time, they can't just simply take a 5 mass object going twice the velocity and a 10 mass object going half the velocity and tie a string between the two things and shoot them off and see if there's twice the energy in the 5 mass going twice the velocity. They can't do any of this. They haven't done any of these experiments. And you're defending this crappy physics that hasn't done any experiments. Zero. Beyond the fake clay experiments of 1735 or whatever, what do you have? Nothing. Okay. If a bullet compresses, so now we're back to the bullet argument. And I just said, look, if we take a spring that's a really long, stretchy spring or something, maybe we can slowly absorb all the energy of the bullet and we can transfer it to the ballistic pendulum, at least half of the energy. If a bullet compresses an ideal spring and somehow prevents it from unwinding, I don't know why it would unwind until all the energy was in the spring, it is storing the momentum in the compressed spring as potential. Well, whatever you want to call it, but of course it's storing the energy is the only word you really need there. So its kinetic energy is greatly diminished because of this. How is it diminished? Its energy goes into the compression of the spring. The spring has the compression, the energy, and now it's going to give it back. The problem is that it's going to be easier to push the bullet than it is the ballistic pendulum. So, but the argument made to you was you lost 99.99% of the kinetic energy when we made it inelastic. So the argument is, if I make it elastic, are you still going to lose 99.9% of the kinetic energy? And I say, of course you can't. But if you do the experiment, you're not going to see any kinetic energy. You're not going to be able to make the ballistic pendulum move more by bouncing the bullet off of it. All right. Is inelastic. It will store the energy, its momentum, because the spring deformation wants to unwind. Well, whatever. We're saying we're agreeing that you're storing the energy. And if we just say that we're going to make a spring as lossless as possible, then what's the outcome going to be? And the problem is, I would argue, is this is the brick wall rubber ball problem, that the ballistic pendulum is so massive that the spring is just going to give the energy back to the bullet in the opposite direction. That is, aside from any calculation of the mass increase being overwhelmed by the velocity decrease, so there's no mass increase. I don't know what the hell that would even be. So I won't even talk about anything of mass increasing. There's nothing, no masses are increasing. Given velocity is squared and the mass is not. Again, this is part of the formula, is destroying the energy. The fact is it's not real energy. That's why you can destroy it mathematically. There's no way to convert from a light thing going fast into a heavy thing going slow and conserve the kinetic energy. You can't do it. All right. It's impossible, because the heavy thing has to go slower because it's got more mass to push. All right, this is what I would expect as a response to your original, now clarified question, which was, do you really think if we could build a spring that could tolerate the velocity of the bullet, that the kinetic energy would be conserved in the ballistic pendulum? Then you didn't answer the question. The question itself is divorced from experiment. How is it divorced? It's the description of an experiment. You can't imagine an experiment that's this simple. This isn't like a light clock or something. It's not like you're, proposing something, way out of the realm of possibility. That we have a spaceship going half the speed of light and we can watch light get bent. That this isn't that reachy. Not unlike Newton's musings on this particular argument. So again, that's a cop-out. The simple fact is there's, what's your argument going to be? Your physics says overtly, if I made a rubber bullet, so let's just get rid of the spring and we'll just use the rubber bullet example, and I bounce the rubber bullet off the pendulum, your theory says twice the energy goes into the ballistic pendulum. That's what your theory says. Okay, so if twice the energy is going into it, twice the momentum, all right, then you should be willing to say that, yes, it has more kinetic energy than if the bullet penetrates, okay, and sticks to the clay. So that's an elastic collision, and your argument is that somehow you're conserving more of the kinetic energy. I mean, you can never conserve it, but you can conserve twice as much of it. I mean, if you can increase the momentum by 2, that's a hell of a lot better, because if you absorb the bullet, you've only transferred the momentum. You didn't make more momentum. But your theory says overtly, Professor Lewin draws it and says it. Okay? And he says, what's it, that famous line he always uses? It's unnegotiable. It's non-negotiable. Okay? Twice the energy has to go into the brick wall. So twice the energy has to go into the ballistic pendulum. These other experiments you mentioned by the end of your video may not prove what you are saying. Well, whatever, says you. Although I think you dismiss the videos provided by Dispar. Well, of course I dismiss them because they're engineered experiments. The very kit this whole thing comes with is intended to do these experiments. It's not intended to do physics. It's intended to demonstrate a phenomenon, and I'm saying that's very shaky. All right. Dispar is under shaky grounds. STEM in action, whatever, the French video, I guess, YouTube channel, do not seem particularly suspect. Well, to you, they don't seem suspect. I would make the logical argument that all you have to do is say, what if? What if the track is a little bit bent? Because you could see that in a sense, right? The one cart that's reflecting loses its energy so rapidly it doesn't even get to the end of the track. It's supposed to be going 1/3 the velocity, and it doesn't even get to the end of the track. It doesn't even hit the bumper. So maybe it's going uphill. And maybe the other one, the other cart that's going way faster than it should be, maybe it's going downhill. All right. As they carry a perfectly acceptable experiment to my eyes. Okay, so I'm just saying, you don't think there's any reason to doubt. Now, you don't have a context here, okay? But for a couple of years now, I've been showing a Professor Lewin experiment where he's doing the same experiment. And frankly, there's blobs of clay all over his air cart. There's every indication, if you look at the two carts, that there's no possible way the one cart weighs twice as much. There's no way you can make it weigh twice as much because it doesn't have enough things attached to it to weigh twice as much, and it certainly doesn't have 4 blobs of clay on it, which the other cart does have too. So again, you haven't, there's lots of reasons to be very suspect of these demonstrations because they are for the purpose of demonstration. They are not for the purpose of let's do the physics in an honest way and find the truth. They are contrived for the very purpose of proving what's in the book. You object to artifacts. I object to anything that gives any reason for suspicion. And yes, artifacts that don't show up anywhere else, well, I'm saying, okay, well, get rid of your artifact, okay, because you shouldn't have any of those. And you certainly shouldn't be showing two charts with different resolutions. You shouldn't certainly be showing a velocity in one case scaled completely different than the velocity in the other case. There's lots of these things you shouldn't be doing if you're going to be honest. All right, and do not get the fact that it shows a bouncing as Newton would suggest. So it doesn't show anything that Newton would suggest. So that's a lie. So fuck you for that. Okay, I mean, I'll do this argument over and over again. Newton clearly stated it. Okay, 1 unit of force, 1 unit of velocity, 2 units of force, 2 units of velocity, 3 units of force, 3 units of velocity. Nowhere does he suggest I can put in 1 unit of force and get 4 units of velocity. Your other objection was that the video does not correspond to the data in real time. I don't think that's what I argued at all. So I don't care how big a delay there is and how the data is presented. That was never an argument. Visually moving different than the plotting. I was arguing that the plot has been rescaled by the software. That's what I argued. And that the 0 point has now been moved based on the fact that the plotting didn't go as high as it wanted to go, and so it got changed. And so it's changed where 0 is. That's what I suggested. But having played the video recording, you must know the video playback and probably the plotting software may have a rate of refreshing that may affect it. Well, whatever. I'm just saying that anything that doesn't happen every other time you do the experiment, I'm saying those kind of artifacts shouldn't be acceptable to anybody. You really shouldn't be scrolling, okay, your chart. You really shouldn't have any need to do that. So the video is complementary, not the primary data source for the observations. Well, whatever that even means. Again, you want to trust these people. That's your business. They won't produce the experiment. So I could ask you another question. So here's another sincere question. Do you sincerely believe that it takes, if I wanted to go, I'm in my car and I'm going to use gas to go 10 miles an hour. And if I go up to 100 miles an hour, do you really believe I'm going to use 100 times more gasoline? Not 10 times more, 100 times more gasoline. I mean, do you believe if I go from 10 miles an hour to, 50 miles an hour, I'm going to use 25 times the gasoline? Come on. So the video is okay. Blah 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 blah. The interments are more precise. I think that's instruments. Okay, instruments are more precise. As you can see, video images create artifacts. For example, so I don't even know what that means or why I should pay any attention to it. I think I'll do the other video separate from this video. But all of these experiments do have variables and subtleties, and they all have to be accounted for. Again, if you're going to use a spring to launch something, you have to calculate, you have to first figure out you're using carts that have angular momentum in their wheels. So you have to recognize that your linear velocity is not your total momentum. Your total momentum is the linear velocity plus the angular momentum caught up in the wheels. There's a lot to this, and this superficial make it look like I'm claiming is bullshit. And the real experiment is the Newton's cradle, for example. Okay, I mean, if you can actually do this experiment. I mean, do you really think this is going to happen? Let me draw that out. Okay, ask you one more question. I mean, do you really think this is how the universe works? And that, you know, it's a good enough question. That it's possible that this could be true, and all of the people who do car analysis and collision, you know, analysis and all that stuff, they're all idiots and full of shit. I think I didn't have that on. Yeah, I didn't. So you didn't see the comment I was reading, but that's not a big loss. Certainly can live without it. So look, their experiment, they're stating this happens. I have 100 momentum in this object. If I give it a velocity and it has a mass, it's a 1 mass. And now I'm going to hit it into a 3 mass. All right. That's standing still. Their theory says, okay, that this leaves with 150 momentum. So I've increased the momentum in this direction. And I'm going to get this extra 50 going back this way. So the net momentum is now 200. So I started with just 100 momentum, and now I have 200 momentum in the system. All right. And now we know that what's going to happen is now we have a 3 mass going here. All right, we have the 1 mass went up to here. And now these two things are going to collide. So this has the 50 momentum here. Okay, is now going this way. And now we have 150 momentum going this way. So this is like 2 cars. So I have 2 cars. I have a heavy car with 150 momentum, and I have a light. They're both going the same speed. So they're both going 20 miles an hour. Okay, 20 miles an hour, let's say. Okay, I'm just making up numbers, but they are going the same speed, the same velocity. When they're at impact, they'll be going the same velocity. All right, and this one has 3 times the mass that this one has. And the total momentum is 200 going into the collision. So you really think I could have 2 cars do this, and then all that's going to come out is the 3 mass is going to be dead, and all I'm going to get is 1 car, okay, is going to leave going 40 miles an hour. And that's all I'm going to get. I'm going to get 100 momentum back. Twice as much as it had here. Twice the velocity. That's it. That's all I'm going to get out of the... So 200 goes in, only 100 comes out. And even if we thought that, okay, these things were deformable, you know, and I'm going to bend fenders and I'm going to crush things, do you really think I'm only going to crush 100 momentum worth? That I can somehow destroy the 200 I have going in, and I'm somehow only going to get 100 coming out? You think that's a viable theory of reality? Do you think that is true? That if they do this experiment, it will do this. It will make free momentum, more momentum in the universe, and then it will destroy the momentum. And then it will make it again. And then it'll destroy it. And then it'll make it again. And then it'll destroy it. Certainly I don't think Newton thought so, and I don't think so, and Descartes didn't think so, and Galileo didn't think so, but whatever. I'm curious. Do you think that really happens? That I can actually have a car crash between a car that weighs 3 times as much and a car that's 1 mass, and they can both go 20 miles an hour and crash into each other, and I just get that 1 car going 40. The light car going 40. That's all I get out. Okay. Yeah, I don't think so. No chance. Okay. So, probably enough of a video. So, till the next time, and such, so forth and whatnot. Thank you for staying in the conversation. But again, yes, how useful this is, I'm not sure. Text is a little bit weak in terms of an argument form. Yeah, it's just not as good as drawings and interactive demonstrations. All right, till the next time and such.